Hello and welcome back to a new C tutorial video here on the Ludwig Fusel channel. In the last video we moved to arrays. So basically an array was one variable that can hold multiple values of the same type. So one variable holds multiple values of one type. In our case we created an array here for our y values. The issue is that for creating an array we needed to require a constant size of the array. This constant size needs to be constant at compile time, so at the time where we build our application before it runs. And this was an issue since we needed to have a fixed value here and we're not able to basically plug in the number on runtime. So basically we cannot depend the size on our array with the count. So if I would try to enter count here, you saw it last video, it doesn't work. It might work on special environments, but at least on the Microsoft environment it doesn't work, and it also makes sense that it doesn't work here. Because C and C++ is all about performance, right? And the idea is basically that you know how your stack is laid out. At a certain point in time, when you are, for example, using SIMD instructions, like these special gaming instructions or vector instructions, how they are called, that can process many data fast. So for example, for matrix calculations, vector computations, all of that stuff, you basically have special CPU instructions that rely on a certain layout in memory, for example. So basically every kind of block of memory that you want to process with these special instructions, these special features, these special fast computation units in the CPU, they kind of have a dependency in memory. They can work on memory that is not dependent. So basically the idea is that they are always on even addresses. So for example, address on the power of or address is a multiplier of, for example, 128 bits or 265 bits or 512 bits, talking about the width of these instructions. So basically the idea is, if you are using these instructions and, for example, they are constrained to, let's say, 128-bit, which is very common, 128-bit, basically 4 times 32-bit, because they can handle 4 32-bit numbers in an example, and basically 4 of these numbers would be maybe 4 by 4, which would be 16 bytes. So basically the idea would then be that the addresses always needs to be aligned on these 16 bytes. So basically the first value that can be processed basically starts here. So this is the first value that we can process, and this value is then going to be 16 bytes big until we basically reach the, I think this should be 10 then. And then we have kind of the second value. So now this is all right, because we are basically always filling up the data. But what would happen if we would kind of try to put one of these data on the stack? Well, basically, for example, if our stack is currently at 0x15, and we basically have here, let's say, for example, a int 8t value. Now, if I would want to try to add a 16-bit with value, we would basically add it to 0x16, to the next empty address, which is an error, because if I would then put my third value on here, this would result in an issue. This is not working. Not working because it's not aligned on these special boundaries, not these special boundaries of 60 bytes. So basically what we would need to do is basically we would need to insert dummy values, dummy zeros, for example, to align the value to the 20 value here. So we would basically waste a few bytes so that we can put the data that shall be used with these fast computations to a certain position in memory on the stack, for example. And all of these mechanics that are operating there are handled by the programming language. So especially when we're getting to C++, there are special data types that have metadata attached to them that basically tell the compiler how it needs to be aligned. So for example, aligned to these 16-byte boundaries here, and then basically the compiler makes sure that the data is always laid out correctly in memory so that we can use these fast computation units. So the idea is that address would be bad. So the address 0x16, we cannot use it. It's not usable because it's not aligned to this boundary. So the boundary is always the case that the last digit on the address here is 0. So the least significant bit, it's called, the last one. That one, if we change one digit here, it has the least impact. It's the least significant bit, or in this case, the least significant hexadecimal digit. This needs to be always 0, so these computation units can work. And what the compiler basically does is it does this all automatically based on the constraints that are around the type, and lays out memory, the stack, and everything else. It automatically lays everything out so that it works, right? And this breaks as soon as we have dynamic allocation on the stack. Because if we have dynamic allocation on the stack, we basically put an unknown number of bytes on the stack, and so all things that the compiler might pre-compute, so how much we basically need to offset. So for example, if I would add in eight values here, the whole stack would then be at runtime be changed. For example, if we have a count of 1, it's just 1. If we have a count of 20, we have it at 20. And basically we are changing addresses during runtime on the stack. And this could work, of course. You can basically take a look at what the value of the stack is and then decide how many times you need to increment the stack to put the new 16-bit value that needs to be aligned on there. However, this all requires computation powers, and C is all about performance. So what we don't want is we don't want to burn CPU cycles checking where in the stack we want to put this value. And so basically we have put it as constraint in here, or this is one reason why we have the constraint in here, which basically tells, well, wait a minute, we are not going to do this dynamically. We want to say this needs to be always a constant number at compile time so that we know how it's going. But actually this is not fine, because we do want to have dynamic memory allocation, right? We want to have a dynamic array size. It works obviously, like no application is allocating like 20 gigabytes when it starts to then basically have all memory available that it needs, right? It's all working dynamic, so basically dynamically when it needs that. And that actually works. We can actually tell and get any memory that we want. So basically we have an option in C and also C++ to basically tell the operating system that we want to have more memory. So by default, and everything that we just talked about was the stack. So the stack is basically everything that is inside of here, starting with the main function where we basically put our X on, the count on, the R0 on, the R1 on, maybe even temporary values from these computations here from that if. We basically also, when we are going into the execute print, we are actually gonna put the line number on the stack. It's not the line number really, it's actually the address of that instruction that basically went into calling this function. We put this address on here so that we know as soon as we are finished with that execute print function where we're gonna go back and continue on executing. This has to do with the disassembly that we talked about, but I don't want to go into the details. So basically the stack is like your working scratchpad. It's really a scratchpad. You start writing on it and you basically start at the top and write yourself down, and as soon as you are done with it, you scratch it away and continue on writing with the data you need, and go back up the scratchpad, back down the scratchpad, and basically just use it as a really fast and efficient throwaway storage, let's say. Throwaway storage. It's always just valid for the function, right? Everything that's in here is going to be thrown away as soon as we return from main. Everything done in here is going to be thrown away when we are finished with f, except the return value, of course. Same thing here. Every of these temporary values, like maybe this address of that string that we have here or anything like that, all of that is basically temporarily loaded, put in a function somewhere, stored on the scratchpad, the stack, and at some point removed when we don't longer need it. In this case, when we are done with our scan-in. Same here, we are having this array here, which we had on the stack. As soon as we are done with execute print, that gets like not erased, but it gets invalidated on the scratchpad, kind of like erased, and we go up a function and continue on with our execution. So scratchpad really, or now I'm also calling it scratchpad like that, but basically the stack, a very fast memory. It's pre-allocated, it has a certain size, we know how big it is, we basically control it. I think I showed this to you, right? When you're right-clicking the application and go to properties, and I think it was at linker system here, stack, committed and reserved sizes. In this case, the default one is 1 megabyte, so 1 megabyte of memory, pre-allocated by the operating system. Set is the stack, we can work with it, build that scratchpad on it, remove it, build it, remove it, build it, and work with that. Working memory for your functions, your all application flow, temporary variables. However, all dynamic data, like data that we need to determine on runtime, where we basically at runtime need to say, all right, I want to have an array of that size. All right, I now want to put that memory in a temporary storage buffer. All right, I want to read a file that is 4 gigabytes, but let's say maybe a file that is 60 megabytes big. So I want to read that whole file into memory and then work on that file. All of these like dynamic stuff, all this dynamic memory that we want to use goes onto a separate storage location, the so-called heap. So basically what we had previously was the stack, and now we have the heap. Stack, basically scratchpad. Function, values, temporary, variables, all of that stuff. everything is going in here. Flow of the applications, the so-called call stack, which functions were called in what order currently, in which function are we currently. Everything is stored on the stack. It is like very fast and consistent. On the other hand, we have the heap. The heap has unlimited size. Just something I should have written in here, like pre-allocated fixed size memory. And the heap basically has unlimited size. Asterisk, caped by OS and system. So of course, if you're having a system with like only 8 gigabytes of RAM, which you're probably not going to have, maybe at least has 16 and even most of the time 32. And basically, as soon as that physical memory is kind of like away, if you have used all your physical memory, the system slows down. The system tries to also supply you more memory than you have plugged in, but this is an advanced topic. This basically means that as soon as you go over like the limit of the system, if you have like an 8 gigabyte system, it allocates 60 gigabyte of memory. This might succeed, and the operating system might write the half of your memories, in this case the spare 8 gigabyte that cannot be put into like the system RAM, the random access memory. It might put this on a disk. So for example, if you have an M.2 disk, which is really fast, this might be even considerable, even through it is way slower than on the normal random access memory. But if you have like an issue in your application, this might run fine because you have a fast storage device, but it's really not a thing you want to have. So you really don't want to overuse your system. But in theory, the heap has an unlimited size, while the stack is basically a pre-allocated fixed size block, right? So how do we interact with the heap? Well, basically the heap is managed by the operating system, in our case, Windows. So if we want to have some memory, so if we need memory, we need to ask Windows. In our case, we now need to ask Windows to give us memory, or ask Windows/DC runtime, because basically C has a uniform way across platforms. And the Windows function is the same, like the function on Linux and on Mac OS X. They're all the same. But basically the idea behind this is that you are calling a function. I already spoiled this. And the function that we are calling is basically a request function that tells the operating system, hey, I want to have a memory of that size. So I just want to have a certain amount of memory for my application of a certain size X. And then I can work with that. Now, how does the stack works? Automatically. So basically, allocation and freeing of memory is done automatically. So basically, we never like deleted that variable. We defined the variable values above here, and as soon as we are returning from the function, that value is no longer accessible, and we can reuse the memory on the stack. This does not work on the heap. The heap is not automatically. We need to manually allocate and free memory. So we cannot really just rely on the operating system cleaning up after us, because basically what we are doing, we are telling the operating system, hey, I want to have some memory. The operating system then locks that piece of memory and says us, and basically gives us the memory. I'm gonna spoil this to you already. It gives us a pointer, of course. So basically gives us a pointer, so the address of the memory that we can use. So basically we go to the operating system and say, hey, give me like 1 megabyte of memory. The operating system takes a look at where it has memory free, and then it basically tells the application, all right, I have allocated you 1 megabyte of memory at that address location, and it's gonna be returned as a pointer. And that pointer, we can then use this pointer to basically store our data. And since I told you that pointers and arrays are like interchangeable, we basically can just treat the pointer as an array, and we can use it in our case in the function as we did it before. So this is basically the idea behind it. And the idea why you need to manually free that memory, so basically allocate and free it by your own, is because the operating system does not know what you're doing with the memory. So it's not related to the stack. So the pointer might travel through your whole application. You might want to return the pointer that you have allocated to like the caller of a function. You might store it somewhere else on the heap. You might store a pointer to a heap on the heap, which itself is again stored in a pointer, which is again stored on the heap, which at some point is maybe stored on the stack. So basically you get my point. Like this memory can be chained together how you like it. The memory can be ordered and managed how you like it. You can maybe create copies of that memory if you want to do it, and you have really a hell of a lot of options with the memory. You can implement your whole own memory management, which is also why it's fast, or faster than like Python or something like that, or Java, which like use an own memory allocator and garbage collector, because basically we're going to take the pointer from the operating system and we manage it on ourselves. So the operating system never knows when we are done with the pointer. We need to manually tell the operating system, hey, I'm now done with it, release the pointer, you can reuse it now. And that's why C and C++ is fast, because we don't have like these garbage collecting algorithms that are basically checking if an object is still used, and if it's not used, it's going to be freed from the operating system and the memory can be reused and stuff like that. But that's basically not the case in C++. So basically we need to tell the operating system, give me memory, and we also need to tell the operating system when we are done dealing with that memory. So we tell the operating system, hey, I'm done, go on and reuse the memory. One important thing, you cannot ruin a computer with that. So basically, if you are allocating 1 GB of memory in your application and you are never freeing it, as long as the application runs, the memory is not usable, because it's like allocated. There's 1 GB that is left blank and allocated by your application, and it's never going to be freed or be available to other applications. Asterisks, of course, because of virtual memory management and paging. So basically putting memory on the disk, it might actually do it, because if you don't access the memory frequently, this block of memory that you have basically allocated at 1 GB, if you don't access it frequently and other applications try to use memory, then the operating system at some point sees, all right, there's memory that has not been accessed by your application. This memory is going to be put on disk. So this memory is stored. So if you don't use it, that memory kind of like that you never have freed to the operating system, it's going to be put away on disk, and you're probably not going to notice it as soon as you run out of memory. But still, it's like counted as used memory on the operating system. But the thing is, if your application closes, the operating system will free all memory associated with it. So basically the operating system will keep track what memory blocks were allocated to your application, and if your application terminates, however it terminates, if it's closed in the task manager, closed by the user, normally terminates, crashes, whatever you do, everything that you allocate is going to be freed. Right? You might corrupt data. For example, if you have a file half written, so you basically took a file, read all content, deleted the file, recreated it, and changed something, but not finished writing all data on that file, of course you're going to have a corrupted file. But that's all about files and in the future. But all of like the resources are cleaned up normally. Like if you have an open handle to a file, so basically if you open up a file and it's protected because you're writing to it and no other application can write to this, as soon as the application terminates, this log is released or should be released. If it's not released, it's a bug in Windows, right? Okay. So the same is with memory. Everything that you and your application use, as soon as the application terminates, it really gets all closed. So you really don't need to worry that you are ruining your computer or anything like that. Everything normally, if you use the application, as soon as it terminates, all resources should be freed. Should be, because of course there can be a bug in the operating system that something doesn't work, but in general we can assume when our application terminates, everything is freed. The only thing that's important when you are programming, especially if you have some for loops or while loops or functions, that you don't allocate on a function call based the memory. So if you're allocating a memory in the function, you should also release it in the same function. One exception is if the memory is used externally. So if you're basically returning that memory pointer that were used in the function, of course you will not free it, because if you free it, you tell the operating system that you are done with the memory, and then it might overwrite that memory and the pointer gets inaccessible, and if you use the pointer, bad things happen. So if you're returning a pointer, it's okay to just allocate it in the function and maybe not free it. This is just a thing for C. In C++, you should always never use a raw pointer to pass it between functions if you transfer ownership. So you should always have a managing class, which is something we're going to talk about in the future, of course. But you should always, in C++ later on, never pass raw pointers. It's okay if you're just in C, but in C++ it's a no-go. So the idea is basically a general rule. You should try to really free all memory that you allocate in the same function. So if execute print allocates the memory, execute print should also free the memory. Except if you know what you're doing and you basically know that memory is returned to the caller, and the caller is going to handle that freeing. But in general, I really don't like the idea of returning raw pointers. Even in C, you can pack a pointer in a struct and then basically have a function like create struct from file, which maybe reads a file and the file contains some configuration, and that's then basically stored inside the struct, as well as the pointer for that allocated memory inside of the struct. And Later on, when you're done with that, you kind of like have a destroy function that destroys the structs and makes sure that all data is free. This is something that I personally like to do, but we're not getting that advanced in this tutorial. All right, so long talking, short story, how to use dynamic memory. So what I basically want to do is I want to have count in here. All right, so the function that we want to use is called malloc, and I'm a bit curious on in which header it's stored, but we can find this out very quickly if we would find a proper documentation, not that. So what did I told you? See, pp reference is the thing that we're gonna look for. That's the one. All right, so here's the documentation for malloc, and it's in stdlib.h. So that's really nice to see. So let's include stdlib.h. All right, and now we should have access to malloc. So how do we use malloc? It's returning a void pointer, and then it basically inside uses a size. Void pointer is just an anonymous pointer. Void pointer basically means a raw memory address that has no type associated. Void pointer, general type, basically means no type, just a raw memory address. And what we always want to do when we basically get a void pointer is we basically want to convert this to a pointer that we can understand. The size in these brackets is the size in bytes that we want to allocate. So if we basically want to allocate that y value array, for that we basically need to use the malloc function here. So now instead of having the array operator, we're going to convert this to a pointer because, right, the malloc function is returning an anonymous pointer, a void pointer. So it is a kind of pointer type. So we also want to have a pointer type here, even it's required because we are using this square brackets operator, the access operator, for giving it an index where we want to basically read or write. And since we want to do this here, we of course need a pointer. We talked about this last video. Then what I also can do is I can get rid of that caping here because we're not going to need it anymore. All right, so now let's use the malloc function. Okay, just call malloc and open the brackets. Now, you would be tempted to just write and count here, right? Because you want to have that many elements. But actually, this is not right. You can already see that Visual Studio is already not happy. It's already yelling at us and saying buffer overrun while writing to y value. It shows actually two errors. First of all, it shows that we are dereferencing the null pointer y value, and it shows us that we have a buffer overrun while writing to y value. Why does it know this? Because it knows that we basically write to count -1, which is 0 to count -1. That's actually okay. These are all of our elements. But the thing is that this pointer that we are basically using here is an int32t pointer, so basically a 32-bit integer. So 32-bit integer means 4 bytes, which basically means that every time we increment I or I -1, so basically from 0 to 1, we basically increment the pointer by 4 bytes. And since this count that we have in here, or the size that goes into the malloc function, is actually in bytes, you can see the problem. So kind of like we are allocating count, but we actually require count times 4. And if we do this with count times 4, the one error should disappear, in theory. Why is it still telling us that we have a buffer overrun? Probably because it doesn't recognize the I -1, but I'm gonna see this in a second. It should disappear as soon as we do something. But it's still giving us a error that we are dereferencing a null pointer y value. Why is it telling us that we are dereferencing this null pointer y value? The thing is that the y value can be null. So basically this pointer could be a so-called null pointer. Null pointer is a pointer to the address 0. And this pointer basically means if you ever get a null pointer, a pointer to address 0, it basically means that the pointer is invalid. It's kind of like common sense that every time a pointer is invalid, it is a null pointer. And basically what the function malloc does is, if it's not able to allocate in memory, there could be some issue there. Maybe it is just too big. If you're trying to allocate like a petabyte of memory, Microsoft is probably going to jump in and say, hey, wait a minute, that's not right. I'm not going to do this. And then it's going to return you a null pointer because it basically tells you, hey, I was not able to fulfill this request. Or if there's really no memory possible, if you use up all your virtual memory, however you want to do this, or anything happens in the operating system, so there was an error in the Windows kernel or in the Windows operating system, which is probably not going to happen, or other bad things will happen, but there might be an error somewhere. Some glitch in the code of Windows, and he was not able to allocate memory. And in any case where like the internals of the malloc fail, no matter in which extents they fail, if this failure occurs, it's going to return a null pointer. And so basically what this what it's detecting here is that we not checked for this null pointer condition. So basically what we want to check is that y value is not equal to the null pointer, which we can just write as a 0 because it's equal to 0. Or what you want to use is, at least in C, you want to use that null constant here. In C++, we're going to have something called null pointer, which you can see doesn't work in C because it's basically underlining that. That's what we're going to use in the future. But for now, I'm just going to use null. Or what we could even do is we could even stripe this down further to just if y value, because if y value will only trigger if this is not 0. So if y value is valid, we're going to do that stuff that we are doing here. Alright, so we still have our buffer overrun, which we shouldn't have. Let's press Ctrl build and see if it goes away. Should hopefully, because there is no issue in our code. I'm not quite sure what it is saying here. Interesting. Actually, this is probably a bug inside of Visual Studio. Alright, so basically this is how you would do this. But long story short, do you always know how big data types are? For example, if we have a struct. If we have a struct as struct D, let's just call it struct D, and if we have like the struct D here with like an int32 A, B, C, D, then we might have like a char XX, we might have a char pointer lol, we might have an int64 T val, we might have an int8 T val set of the size 20. So tell me how big this struct is. How big is the struct and how many times would we need to multiply count to allocate data for that struct? Right? Nobody knows. Really, nobody knows how big the struct is. Especially because like the compiler might actually align the struct and make it bigger than it might need to be to basically assert that the stack is like always, and also the heap memory is always aligned properly. So how can we tell how big that struct is? Well, actually there's a function. It's not really a function. It's actually like something that the compiler evaluates, but there is a thing that we can use, like a function that tells us how big any data type is. It is called sizeof. Sizeof works like a function, but you can see it's not looking like a function. It's more looking like this void struct char. It's basically blue, which basically tells you that it is a built-in C construct. So basically sizeof is actually being directly computed by the compiler. So what I could do is a sizeof struct D, for example, and if I would do this like that and hover over that, you can actually see that it is resolving to 64 UI64, which basically means it is 64 bytes big and it is stored as a 64-bit integer. So basically sizeof is always going to return you the size of that data type that you have given it in the system path with. So on a 32-bit system, this would return you a 32-bit integer, and on a 64-bit system, it's returning you a 64-bit integer. And in our case, it's also returning 64 because the struct D is 64 bytes big. But we don't really care about the struct, we're caring about the uint32t. And if I would hover over that, you can see that it's actually 4 UI64, which basically means 4 byte, and it's a 64-bit value. So we can basically tell it that we want to allocate a int32t, we want to get the size of that to basically get the proper byte value, and we multiply this by count, which basically makes it makes as many slots in this array or in this heap allocated array, pointer, however you want to call it, like the user implemented or given by the count value. And I still don't know what's going down here. This shouldn't be an issue. It's probably a bug. So the idea is basically the malloc function is returning a void pointer. C is not very strict. So basically C automatically converts this void pointer to an int32t pointer. But on C++, it's not going to be able to do this automatically because C++ does some type checkings more than C. So basically what C++ tries to do is it tries to basically convert an void pointer to an int32t pointer. But there is no conversion defined. You can define an own conversion, but by default there's no conversion defined between the void pointer and the int32t pointer. So basically what then we basically need to do is we need to manually tell it, hey, convert this no matter what. And we basically do this by a so-called cast, and the cast is basically done by opening up brackets somewhere. So basically that is the expression that we want to cast. So that expression that I now have marked is a void pointer, and what I basically do is I put the cast before that expression here, so some brackets before that expression, and inside of these brackets I basically write the type to which I want to cast this, which in our case is a int32t pointer. And if I do this like that, it's also going to work in C++, but on C it's not really an issue. So that is not really required. So I can just leave it away for the C way. But that's just a side note for C++ later. All right, so I know that my code works. This is why we're going to jump into it and just quickly execute it and see if it works. So let's see. Enter an integer value, 5. Enter another integer value, 2. Okay, 55, 155 works. Let's try it out with a bit more values. 10, 20. Yeah, looks legit. 155, 305, 505, and so on. Looks good. Let's try it out again. Let's maybe say 5, and now 999. 999999999. Enter. Okay, the value was so big. It was not able to deduce it. I always went over that. This basically was converted back and resulted in a negative value probably. But let me maybe put a few big values in here. 1, 2, 3, 4. 1, 2, 3, 4. Should be good. And now you can basically see that it's now crunching memory. And actually, if you take a look at the side, you can actually see in that graph that we have one big jump here in the process memory. If I quickly pause that, you can basically see that at the start, we were here low, if I hover over that, at a memory usage of 616 kilobytes. So this was basically the memory usage until we called malloc. And as soon as we basically called malloc, we requested more memory from the operating system, which we can see in this nice visualization of Visual Studio. And it basically jumps up to 383 megabytes of memory. So from a few kilobytes to a big amount of megabytes. So basically the malloc requested that memory actually from the system. And then it's going to crunch on that and print everything. So the computations are already done when it starts crunching there. And if I would maybe now also to show this to you, go into my execute print function here. You can also see that the y value is actually an int pointer here, and there is some data attached to it. For example, the first value is the 55. You cannot see really more here in this browser here because it's really not recognizing this as an array. It's basically just seeing this as a normal pointer. You could try and trick Visual Studio into thinking it's an array. You can, I think, write this like that to access certain values. So what I basically can do here is you can see I can put this into brackets here, write y value, and use the array operator to basically access any member of that array. So I basically can go to watch 1 here in this case and write any expression that we do. We have another option to actually take a look at this. You can actually double click that value, copy that value, then you can go to debug, Windows, where is it? Memory 1. And if you're opening this memory 1 tab, it's spawning at a really odd location. And I personally like to have it down here. So I drag it down here. And what this basically is a whole view of the memory. So basically all memory that is available to your application, you can basically inspect it here. And if I paste in the address that I just copied, you can basically see that we are now here and getting a hexadecimal representation of these values. They don't really look promising because it's not really properly formatting them, but you can at least take a look at the memory that we have allocated. So scroll through that and enjoy that madness that's going on. Of course, all hexadecimal here. What you can also do is do something like y value, and it will automatically jump to that address. So I could go to address of count, which will automatically go to the variable count, which is probably now inside of the stack somewhere. And if I would scroll a bit up, you would see other stack values as well, but it's really useful later on. If you're later on trying to debug something, this memory view can come into hands. It's not really useful yet, but I want to show it to you so that you know what you are dealing with. And if you're really interested in a certain value of y value, you can always like write it here. Y value of 2 is 305. So helpful tool for all your computations. Now I can go in and continue on the madness of printing their stuff. Alright, so now we are done, right? Are we done? No, of course not. We have forgotten something very important that I told you right at the beginning. Releasing the memory. I know you are now getting epilepsis from that view, but that's how things work out. Okay, no, let's stop this. So memory that are allocated here, we need to free it. Where do we need to free it? We need to free it here. Free. Why do we not need to free it here? Because basically if we get null pointer, there's nothing that we can free. And basically that's why it's inside of these check if it's not null pointer. But basically the free should be always here, and you should be really, really concerned that you don't have a return in here. In C++, having multiple return statements is totally fine. In C++, you can return from multiple points because everything should be wrapped into an object, and objects clean itself up automatically. Only if you provide the functionality, so the author of the object, but we're going to later on when we go to C++ see that we're going to provide our own. cleanup routines for objects, and that everything works out automatically. But in C it does not. So in C you should always have one return statement or none in case of a void function. Not multiple ones, especially if you're dealing with memory. If you have a little util function, it might be good to just, for readability, just write two return statements. Totally fine, but as soon as you're dealing with memory, you should have one return function, because if you're having a return function, for example, inside here you have something like if error return, something like that. If you have something like that in this function here, it will basically return here without going to that free statement, which is bad. You don't want to have that. If you want to really check for error, then you can add another condition here by adding these double ands, which is basically doing a logical operation on two Boolean values, on two Boolean expressions. Boolean expression here, which asserts the count, and you can basically say not error here, which will basically introduce a second condition to that for loop, and as long as this error is not present and I is smaller equal count, this for loop will loop. As soon as the error condition is met, it will basically jump out of the for loop, or if the count plus 1 is reached. So count is like it's bigger than the count, I is bigger than the count should be, then it's also going to jump out. So you can always chain multiple together if you are needing that. Alright, so how do we free? Well, we could consider taking a look at the documentation, and the function down here is called free. It's just called free and it's frees memory. Right, very simple, very straightforward. So what we basically want to do is we want to call it free function with the y value pointer in here. Now let me add some breakpoints. We're going to add a breakpoint here. Before that malloc, we're going to add a breakpoint here before the free, and a breakpoint after that freeing. I'm going to press the local Windows debugger, and we're going to profile a bit what memory does. So 5, and let's maybe do 10,000 values so that we see how it's doing that. And what I basically now want to do is I want to now enable heap profiling. Heap profiling basically allows you to track memory usage of your application, and I'm going to enable this by going to this diagnostic tools. Let's maybe make this a bit bigger now, and click on that enable heap profiling button. As you can see, this affects performance, so the application will run slower if this is enabled, but it helps you taking a look at your heap. So I'm going to click on that, and it's gonna lag a bit. Come on, do it, enable it. Okay, there we have it. Okay, enabling heap profiling needs a rerun. I think this is new, or I actually haven't used it for a while, heap profiling. It might be that it requires a restart of your application. Okay, but if I restart your application, heap profiling is enabled. Yeah, okay, nice. So 5 and 1, 2, 3, 10,000 again, and now we are here at that breakpoint. Now what you want to do to basically track your memory usage, you basically want to take a snapshot. By clicking on this take snapshot button, you're basically going to get a snapshot here. We basically can see the number of allocations. So in our case, we have currently 201 allocations. These allocations are just coming on how the operating system called of our application. You can actually see that the size of the heap is 53 kilobytes. Now what I'm basically going to do is let me make a breakpoint here for before that if, and click on continue, so that we are basically advancing that. We called now malloc, and if I would now take a snapshot again, you can see that we are now having 202 allocations, and that the difference in the brackets is +1. So basically we have added one allocation to that heap. It's okay, because we called malloc once. So one time call of malloc, one new allocation on the heap. You can also see that we have a bit more size on the heap. Now we have 92 kilobytes, which is a plus of 93 bytes. And we could actually do the math here. Let's go into the calculator. Come on, calculator, and let's do it. So the int was 4 bytes, so let's go into the standard, scientific. 4 times we had a count of 10,000. If we do this, we have like this 40,000, and let's now divide this by 1024, which is basically bringing this to kilobytes. And now you can basically see that the exact memory that we would expect is 93.06 kilobytes, but it is 93.11 or 11 to, I don't know if it is it in English the same if you're having something like after that delimiter here? Are you basically telling it that it is a Is it 11 or 1-1? In German, it's 1-1 and not 11, but yeah, it really doesn't care. The thing is, it's always going to be a bit bigger because we have all these debug checks around. So all of that instrumentalization is going to detect if we write out of the memory. So if you are corrupting the heap memory by writing over the requested size, it's basically detected because it's a bit bigger. So basically, if you're on debug, it's always going to allocate more to runtime check your memory usages again. Now, basically, what we can do now, we can actually click this +1. This is going to open up this this window here, and it's basically showing you what you have allocated. You can basically see that the object type that has been allocated is a void object. Yeah, it's a void pointer, and it is of the size 4000 bytes. You can actually see this is exactly what we calculated, 4000 bytes. So this is basically what we requested as an allocation. You can also go to the stack, which is basically showing you where it allocated that, and you can basically see where the memory allocation was. So on the heap, we have an external frame, which is basically Windows, and Windows itself has no allocations. However, there is this main CRT startup. Main CRT startup is actually the entry point that Windows calls. So this is something that is generated by the compiler, by the Windows runtime libraries. It's called main CRT startup, and as you can see, it's allocated by Windows, and you can see that the difference in heap allocations is 1, which is basically our allocation here. We can open this up even deeper. You can see that we are going one level deeper into SCRT common main. SCRT common main is also something provided by Microsoft, which is calling SCRT common main SEH, which is also provided by Microsoft, which is calling a invoke main function, which is also invoked by or generated by Microsoft. And then we are finally at our main function. This is our main function now. Our main function has the scan int and the execute print function. In our case, we are +1 on the execute print. And then you can actually see that in the external frame of that execute print function, we have one allocation, which is the allocation we have now done. So really helpful to show us what's going on. All right, so let's hit continue again and let the application do its work, and see as soon as we're getting to the tree. Now I could take another snapshot, and you can see while we were computing and printing the values, we had no allocation on the heap, still the same number, no plus, no new memory, everything's still the same. But what happens if we are now calling free? And take a snapshot again, can now see that we are back at 201 allocation. It's -1 allocation that we have done, same size than we allocated previously. If I would open this up as well, you can also see that we have a new object that has been allocated, or in this case minus allocated, so -1. So the difference was -4000 bytes, and the allocation that was done is 0 bytes. We have not allocated anything, we have freed something. And again, if we would go into the stack, we would have that Microsoft madness until we get to our main function. And again, in the execute print function, we have in the external frame the -1, which is basically telling us that free was executed in our execute print function. And now with that free in place, we basically are now experts of the heap. And basically that's all you need to know about the heap. You can allocate with malloc, and you can give data back with free. And that's really everything you need to use. On Microsoft, there are special types of malloc that guarantee you to give you aligned memory. However, you can implement this all on your own. You really just need malloc and free. Everything else can be built on top of these functions, which might be provided by the operating system as well, but you can implement everything on your own, right? So yeah, that's actually it for this video. Everything you need to know. Let me quickly summarize. So malloc is basically allocating a block of memory of the size in bytes you're going to give it as a function parameter, and it's going to return you the memory as a so-called void pointer, which is just a plain address that you can cast, or just in C case convert to any pointer value you like. In our case, we use the in32t pointer, and we use the size of function to basically get the size of one single element of in32t, which is basically 4 in our case, and then we multiply it by count to make an array as big as the count that the user inputted was. So we dynamically generated an array of a certain size. We checked if the array is valid, because this malloc function can return a so-called null pointer. So we're always going to check if it's not equal to null, or null pointer is equal to the address x0x0, or in short case just 0. But because we are checking to 0, we can just leave the comparison away and just do the plain if. Down in the if itself, we can use that pointer that we just gathered, similar to an array, completely the same. Syntax is the same. We can read it, write from it to it. And Microsoft is complaining about things because it's dumb and doesn't know that our code is correct, which is really sad. But yeah, that's how it is. Really, nobody's using C these days, so probably, or at least like in a Microsoft environment. But that's probably the case why it's complaining about that. But yeah. So you basically use your array or your pointer as you would use any normal pointer or any normal array. It really doesn't depend in the terms of how you write code. If it is on the stack or on the heap, it's just a plain pointer. You can use it however you like. You should probably not discard it or to pointer arithmetic so that the pointer gets away. You should always store like your initial pointer value, of course. But get the point, yeah. You can basically do whatever you want to that memory. Use the pointer however you like it. Only thing you really should care about is that you free it after you're done with it, and ideally free and allocate or malloc and free should always be in the same function. There's one exception if you're returning that new allocated memory pointer because it's been required by the application or by the caller of the function, then it might be okay to not free it if you can guarantee that the caller will free it. But it's an issue that we're going to completely solve in C++, so stay tuned for that. Alright, so that wraps up the video for today. Hope you enjoyed. It was a bit longer than I expected, but yeah. Hope you enjoyed, hope you learned something. Make sure to like and subscribe, and see you on the next video. Have a nice day. Bye.